So just after World War One, science has come off its break, and de Broglie has a hypothesis. He compares light to electrons, and he said that all matter, like electrons, have wave properties. He based this off of light, which is mostly wave, but has particle properties, and he said that matter, which is mostly particle, should have wave properties. He substituted the speed of light in Einstein's equation for velocity instead, as you can see. Problem was that this hypothesis right here, although it claimed to be true, had no proof until years later when Davison and Germer conducted an experiment. Done. So in 1927, Davison and Germer proved that there are similar properties between waves and electrons. They used an electron beam, which eventually were diffracted. Now, at this point, we thought that only waves can be diffracted. They performed this experiment in a vacuum to avoid the electrons colliding with other matter, but it was only when air was let into the vacuum, which accidentally created a crystal oxide, allowing the nickel to diffract the electrons. Now, this was kind of weird because, like I said, we thought that only waves can be diffracted, and this was when scientists first realized that de Broglie's hypothesis was true, and that the electrons clearly do have wave properties if they're able to be diffracted. Now, Thomson, he also did the same thing, shooting electrons at tinfoil, finding the same results. So another example stating that light and matter can both be classified as waves and particles to prove de Broglie's hypothesis was Claus Johnson and his double slit experiment. In his experiment, electrons were shot at a screen with two slits, and the angular pattern of the electrons after they passed through was measured. And the electrons were proven to have the same interference patterns as other waves like light or water. You can actually imagine, as we've all seen, like a raindrop drop into any kind of water, and it ripples out, it creates a ripple effect, and that's the same kind of thing that the electrons did. So clearly they're acting like waves and obviously have wave-like properties. So on the journey to the atom, we are about to learn about the electrons and their patterns, their wave patterns. But first, we got to know a few things. You need to know what diffraction is, which refers to the interference of a wave when it comes into contact with matter. You need to know what matter is. It's anything with a mass, electrons, protons, any substance, anything you can touch, even things that you can't touch. The last thing you need to know is what a wave is, and a wave is a transfer of energy without the transfer of material. There you go.
Good luck.
De Broglie's hypothesis stated that diffraction was not a property exhibited by waves only, but that particles such as electrons could show the same properties. When Clinton, Davison, and Lester Germer fired electrons at a crystalline nickel target, the angular dependence of the reflected electron intensity was measured, and it was found that it had the same diffraction pattern that Bragg predicted for X-rays. He greatly advanced the knowledge of the physical nature on the atomic scale and also received the Nobel Prize on his wave nature of electrons discovery. De Broglie also said that waves produced by electrons contained in the orbit around the nucleus set up a standing wave of certain energy, frequency, and wavelength. Electrons can act like waves, which answered many questions about electrons that we weren't able to answer before he discovered this. So de Broglie's hypothesis suggested that, like light, electrons could act as both particles and waves. And no one believed this, as Keegan had said earlier. Everyone thought he was a little bit crazy. But then through experiments like the double slit experiment and the electron diffraction experiments, it was proven that he was actually correct in thinking that electrons could act in both ways. To show you this, and the way he advanced the atomic model was originally Bohr, Rutherford. Their model had perfect circles in orbits, in which the electrons lived or stayed, if you will. But after his hypothesis, it was found that they could actually act in any way and be in pretty much any shape. So it's pretty much just a big scribble. But
problems with the results of de Broglie's research were mainly that he couldn't really prove his own hypothesis at the time, not necessarily the results themselves. He could theorize all he wanted that particles had wavelengths, but he had no real way of proving this using his physics in the time of 1923, as it was very underdeveloped. It was a very bold new theory and was not widely accepted or respected in the scientific community in its early days. So basically, there wasn't necessarily a problem with the results, but just being able to get his theory off the ground, it was a struggle because not many people believed it, and it wasn't widely accepted. So even just getting other people to want to work with him and to try to find the evidence was his problem, not the actual results, as they were later seen to be basically true after the Davidson and Germer diffraction experiment. Davidson and Germer's results from their experiment were very solid. Their only problem was not truly understanding what it meant. They understood diffraction was occurring, which meant the particles were acting as light, but not much was understood about diffraction at the time as it was a relatively new topic. Therefore, their results proved de Broglie's hypothesis, but the problem was they couldn't use this information to discover or to learn more about the particles or to further contribute to his theory, but rather just to show that it was true. If more was known about diffraction, they could have used that to increase their knowledge, however it wasn't. So basically their problem was the standstill they were at in that time with the knowledge that they had, and they couldn't use that to further develop the theory anymore. Lastly, the results of the double slit experiment definitely had some problems. The electrons shot through the double slit were seen to act and interfere with each other the same way waves did. However, when a wave of light or water would pass through the slits, it would pass through both at the same time as one large unit. Electrons as single individual units cannot pass through both slits at the same time, obviously, it has to be one or the other. So this left the question of why or how the particles were behaving as waves, because they couldn't pass through both slits like a light wave or a water wave would. It was also seen that when one slit was closed and the other was left open, the interference pattern from the electrons would disappear. So the pattern the double slit experiment formed couldn't be explained by particles bouncing off the sides of the slit because of this. The problem with the double slit experiment was that it begged the question as to why the particles were acting as waves if they weren't passing as one large unit, but rather a bunch of small units, and either through one slit or the other. The problem is why this is happening.
So, time for interesting facts. My fact is that de Broglie's hypothesis, when nobody believed him at his university, as it was his thesis, and they told him he was stupid, he sent it into the one and only Albert Einstein, who wrote back to his professors and said, "You guys are stupid." How cool is that?
You still recording? You recording? Fun fact number 2. Davidson and Germer accidentally stumbled upon their diffraction experiment while doing something else. During an experiment they were conducting, air entered their chamber when they were shining a laser off the surface of a nickel, which created an oxidized surface on the nickel they were working with. To fix this problem, they heated up the nickel to an extreme temperature, which created crystal areas and planes on the surface of the nickel, which caused the diffraction, and was basically how they stumbled upon their diffraction experiment.
I said mine earlier, but he won the Nobel Prize for on his wave nature of electrons discovery. Yeah, it's not as interesting as theirs, but that's pretty much what I found. So.